Alright, hello everyone. I'm here to go over some of the test questions that people seem to have trouble with. This may all come out in one video or maybe a series of videos. But just gonna start with question 4 here. So I'm trying out a new writing on a tablet tool. So these equations may be a little messy, but you can always look for the official versions on in your textbooks or in Sakai. But so everyone, I think, pretty much understands drdt. So the change in our position over time, and it is a differential, is equal to v r, or our velocity over time. Let's see here. I should move these things a little further over so that we don't get confused. Alright, sorted that out. So derivative with respect to time is our velocity. And then the next step, our derivative of the velocity with respect to time, which is then the second derivative. You could also think it is the second derivative of our position with respect to time, is equal to our acceleration. We could call a of r over here. So yeah, I think everyone pretty much got that. But then the next steps were a little bit more challenging, a little more inconsistent between a lot of you. So the average velocity vector during the time interval. All right, so this is actually trickier than it might seem. And my first thought was to do it a complicated way. We can take our velocity vector, which will have both I and j components, and we can integrate it from 5 seconds to 2 seconds. And this will absolutely work. It's just a little complicated, and I needed to remember. Well, I didn't need to, so that's an option. What I could have remembered, though, is that if you're asked for an average velocity, then you can always just do the change in displacement over the change in time, which will always work for average velocity. That's what kind of got a lot of you with the last question. Is the average velocity is the change in distance or the change in displacement, not distance, so displacement, very important, over time. Therefore, with the last question, if you're taking a car somewhere and then coming back to your original position, your velocity, your average velocity is 0, or was 0, because you had a net 0 distance. So you go all over space, but your average velocity was 0, because the two directions kind of cancel out. So yeah, that tripped a lot of people. And also, what you can't do, if I believe in this vector, you will get a velocity that is not linear. You can't do final velocity plus initial velocity. You can't just average them because it's not a linear relationship. If it is a linear relationship, then you can average the final velocity, the velocity at 5 seconds, and then the initial velocity at 2 seconds. But you cannot do that if you don't have a linear relationship, which you won't. So these are our two correct options. Then the other problem that I saw, where have I gone? Hold on a second. I had to remake it. I might experiment with different shared, like, whiteboard type things as we go along. But the other thing that I saw trip people up was the vector versus magnitude. So a vector has two directions. We can imagine little carrots on top of I and j the way they are here. So it has a direction that we've designated I, oftentimes that'll be x, and it has a direction we've designated j, oftentimes that will be y. So we have 4 units in one direction. In fact, I'm going to go ahead and change that to a 5 since that's consistent with the problem below. But this would be a position vector of 5 meters right, or in the I direction, and 6 meters up. And in fact, going to make that 6 meters down. Correct myself, but also showing how it works. So now, likely we make the negative direction down. So now we have a vector that's 5 meters up, or 5 meters right, and 6 meters down. In fact, I can make a thing real quick. Do something like this if the origin is where it starts. I think most of you get at least conceptually vectors, but then the actual mechanics of turning this vector into a value. So some of the questions ask for a vector, and I think most of you did those fine. But then the last one asks for a magnitude, and you'll be able to find a vector following these procedures, which I think most of you did pretty well on, but come to me with questions. But then you need to turn that vector into a number, a value. In this case, it would be a value in meters. For acceleration, it would be a value in meters per second squared. So, do this, we need to do a squared plus b squared is equal to c squared. So quadratics, it's like a triangle where we have, let's call this side A and this side B, and this new side B. And so with a right triangle, this side A, this side B, a squared plus b squared. To get the length or the magnitude of this third side, it has to be c squared. I think a lot of you were using that formula, but there might be, with how you plugged it into your calculators or what I saw written down, there was a little bit of confusion. So, we have 5 squared plus negative 6 squared square root for the magnitude of our vector. And what I think I saw a lot of you do is you would turn this into a negative 36, but when you square a negative, that's negative 6 times negative 6, a negative times a negative is a positive. We wind up with 25 meters squared plus 36 meters squared square rooted. Don't know why that was coming about. Maybe some of you forgot. Maybe it's how you plug in your calculator. You need to make sure you put the negative 6 meters in, well, I guess it would just be negative 6 in a calculator. You got to make sure you put the negative 6 in parentheses before you square it, because otherwise the calculator won't know. It will square 6 and then make it negative. So maybe that's what was happening. I can only conjecture. And then, so you have a new value, which you have to square root. I didn't pick nice number, so this is just 61 meters squared, or square rooted, which gives us about 7.8 meters. And so, that is the basics of this problem. I might provide the actual solutions later, but yeah, that's one problem down, more to follow.